Okay, I am going to go over the problems in my fall 2021 midterm for AI. So let's take a look at the contents of problem 1. The backstory, Rowan has just opened a new swimming pool that is surrounded by black and white tiles. On sunny days, the black tiles get very hot, and so people only walk on the white tiles. It's called Sunny Summer Swim Days, Hssd. Here's the game. You control one player on a rectangular grid that is A units high and B units wide. For example, figure 1 shows one sample game where A equals 7 and B equals 6. So here's one sample game. You can see the key for player. That's a hot tile, cool tile, and pool tile. And it's A by B, right? Different games may have different layouts, but before the game starts, you're given a map that specifies A and B and also the type of each square on the grid, i.e. if it's hot, cool, or pool. So before the game starts, you are given a map, right? That's useful. As shown in figure 2, player can move in any of these 8 compass directions. All moves cost 1 point. If you move onto a hot tile, then the game is over and you lose. If you move on to a cool tile, you keep playing. If you move to a pool tile, the game is over and you win. Object of the game is to find an optimal route for the player from the starting location to the pool. Note that there may be multiple optimal routes. For example, for the game shown in figure 1, there are 4 optimal routes, all of which cost 3 points. So let's see, northeast, northeast, north. So you start here, you go northeast, and then north. That's one route. Or you could go northeast, north, northeast. So you could go northeast, then north, then northeast. You still end up in the same place in the pool. Northeast, north, north. You go northeast, north, north. So clearly it doesn't matter which pool tile I get to, just have to get to some pool tile. Northeast, northwest, northeast. So northeast, northwest, northeast. There you go. So all of those cost 3 points. Okay, so let's see if you can still see all of the questions on the camera. I'm not sure if you can. Okay, I think you can see everything. So, suppose you're given the map for an A by B Hssd game, right? So just, some random A by B, along with the start position for the player. Here, I'll move this down a little bit so you can see the map a little bit. What is the size of a minimal state space representation for this problem? To get full credit, you must justify your answer. So for this starting problem, really all you need to know is where is the player, right? And if you know where the player is, you will know whether you have already won, already lost, or and so the game's over, or you're still working on it. So really all we need to know is A by B different states based on where the player is. So I'm going to say A times B states because because there are that many possible spaces on the grid where the player can be, and all I care about is the player location. Can you see what I'm writing down there, right? All I care about is player's location. All right, question 1B. Now, I will say that you could do things like, I could collapse all of the pool squares down to 1 or something, and you could do that, but really this was all I was looking for. And then, what are we doing here? There we go. I can almost see the paper, and I can almost see it's really not the best setup here. Anyway, suppose you're given the map for an A by B, so same size Hssd game, this game, but you are not given the start position for the player. Does the size of a minimal state space representation for this problem differ from that of the previous question? If so, what is it? If not, why not? And the answer is that, if the, the answer is no, right? It does not, the size of the state space does not change, only which state is the start state. Right? Okay, so let's talk about problem 2, which is hazy summer swim days. On hazy summer swim days, the black tiles don't get quite as hot, so it's okay to step on them once in a while, but not 2 in a row. For clarity, here are a list of all the rules of Hssd. These are the rules for Hssd that are the same as the previous one. You control one player on an A by B grid. Before the game starts, you're given the map that specifies what each square on the grid represents. Before the player can move in any of the 8 compass directions, the player can move in any of the 8 compass directions, and each move costs 1 point. If you move onto a cool tile, you keep playing. If you move onto a pool tile, then the game's over and you win. And the object of the game is to find an optimal route from the player from the starting location to the pool. So that's all the same as before, but we've got some new rules now, which is you're now allowed to move from a cool tile onto a hot one, right? So you can move from a cool onto a hot one. If you do so, the game continues and you just keep playing. But you may not move from a hot tile onto another hot tile. If you do so, the game is over and you lose, right? So before you lost when you stepped on 1 hot tile, now you lose if you stepped on 2 hot tiles. Once you get into the pool, you've already won, so you'd never move from the pool to a hot tile anyway, all right? So where are my questions? There we go. I can still see this on the camera. You would not believe the size of the screen that I'm looking at for this recording, but whatever. Suppose you're given the map for an A by B Hssd game along with the start position for the player. What's the size of a minimal state space representation for this problem? Get full credit, you must justify your answer. So we still have A times B possible spaces, right? But now we need to think about, is it the first time I've stepped on a black space or the second time I've stepped on a black space, right? So what I'm going to say is we have A times B times 2, right? Where you can think of, essentially we need, oops, that doesn't say need. And it's always important to write neatly when you're taking an exam. We need A times B states to represent let's say having just left a white space, right? So the first time you land on black, you're okay. So all of these spaces are sort of, if we start there, it's like we just left a white space and we're in the pools. Oh, you can't see that, can you? If we start there, it's like you just left a white space and you're in the pool, right? If that was my starting position, I just win automatically. If I start there, it's like I've just started on a white space. And if I start there, it's like I previously was on a white space, but now I'm on a black space. So it's the first time I'm on the black space, right? And so we need to represent A by B states, having to represent just left a white space, I suppose we could say, or just started. Plus another A times B states to represent having just left a black space, right? So if we leave a black space and then we go on to another black space, we're in trouble. But if we leave a black space and we go on to a white space, then we'd be okay. So if we have A times B times 2 spaces, we should be fine. And then the next question is, suppose you're given the map for this game along with the start position for the player, but the costs of the moves are changed. Right now it costs 1 point for a vertical or horizontal move, but 1.5 points for a diagonal move. Does the size of minimal state space representation for this problem differ? And the answer is, again, no, it doesn't differ, because what will change is the weights of the transitions between states but not the number of states. Or actually the transitions that you make, but really we care about is the number of states. So we'll just leave it as that. And just to explain this a little bit better, so we need A by B states to represent having just left a white space or just started, plus A by B states to represent having just left a black space. And the idea here is, you know, if you think of it as sort of a two-layer checkerboard, right? If I go from here on layer 1, I'd end up here on layer, well, sorry, I'd end up here on layer 1, which is my first time being at the being on a black square. But when I leave this square, I'm going to go to somewhere else on layer 2, which might be a white one or it might be a black one, right? And there are other analogies you could use to explain what's going on here. Oops, you can't see it again. To explain what's going on here. But the general idea is you need to be able to figure out whether you're sort of no problem or pending doom or actually gone. Okay, so part 3 of this game takes pretty much the same rules we had before, but now we are adding some toys, these ducks that are in the picture. So most of the rules for this game are the same as in Hssd, except that before you get into the pool, you need to pick up all the pool toys that are on the tiles outside the pool. For clarity, here's a list of all the rules, and then I have a list of all the rules, right? You can there's the rules that we had before. You control one player as on an A by B grid. Before the game starts, you're given a map that specifies what each square on the grid represents. The player can move in any of the 8 compass directions. Each move still costs just 1 point. Cool tile, you keep playing. Hot tile from a cool tile, you keep playing. Hot tile from a hot tile, the game is over and you lose. So we still need sort of the extra layers for the for whether you're doomed or not, as it were, right? And then the new rules that we have are the game starts with T toys on T different tiles. Toys never start in the pool and they never double up. When a player gets to a square with a toy, they automatically pick it up and they never put it down. If your player moves into the pool before picking up all the toys, the game's over and you lose. If your player picks up all the toys and then moves into the pool, the game's over and you win. The object of the game is to find the optimal route, so the player picks up all the toys and then goes into the pool. So if we think about what we had before, in the initial game, we needed the A times B states to represent our full map, right? And then in the second version, when we had this, you can step on a black square, but only once, we needed sort of an A times B and an A times B. Can you see this? But each time, there were sort of the 2 layers depending on whether you had stepped on a black square before or not, right? And what we need to do now is we need to think about, have you picked up a duck, right? And sort of where is there still a duck, so, or a toy. So as soon as you pick up the toy, right, you automatically pick it up and put it down, but you need to keep track of where the toys are, right? So if we think about it, we have these 2 maps, right? And then for each of our toys, we need to have a map where the toy is there and a map where the toy is not, but we need that for each of these 2, right? So previously we had 3 times 2 times 2 choices, right? Because we had not 3 times 2. Why do I have 3 times 2? We had A times B times 2 choices, right? For these 2 layers here. And now the question is, how much more do we need for the ducks, right? So let's just think about the A times B for a minute, right? And let's forget about this other one for a minute, because whatever we figure out for the A times B, we're going to have to also do for this one. So what do we have here, right? We have, let's call these, I'm going to call this first duck, let's call it D1. I don't know why I put the arrow that way. And I'm going to call the second duck D2, okay? So for each case that I need to think about, right, I'm going to have a case where I have D1 and D2 still on the board, right? So I need to pick them up. I'm going to have another sort of version of the board where I have maybe D1 picked up but not D2. Another version of the board where I have D2 picked up but not D1. And then a final version of the board where everybody's been picked up, right? And now I can head for the pool. So really, sorry, it's telling me I have class very soon. So what's going on here? Essentially, I need 4 additional copies of each of these, right? So one thing that I can do is I can just say times 4, right? That's kind of the answer. How do I think about this? Well, another way to think about this, yes, by the way, that's my answer. Another way to think about this is that I need to keep track of a Boolean for each duck, right? So when I'm thinking about how do I name my states, right? My state is going to have to do with I have A times B possible locations on any given board. I have 2 given boards. I need to know whether I'm in sort of I've already stepped on a black space or I haven't stepped on a black space most recently. And then I need 2 times 2 more bits. I need a binary true false that tells me, did I pick up duck number 1 and did I pick up duck number 2? And so I end up with times 4 here. Okay, so for 3B, the same crazy hazy summer swim days with the toys, right? But it says you decide to use A-star search to win at the 2 toys Hssd game. Your first idea for heuristic is the following. The heuristic of S is, and this is the Manhattan distance I explained, right? Manhattan distance between the player and toy 1 plus the Manhattan distance between the player and toy 2, where P equals player location, T1 is the location T1, T2 is the location of T2, and it says note that a toy's location will be the same as the player's once the player has picked up that toy. And then I define Manhattan distance here, but hopefully you know what Manhattan distance is anyway. Anyway, but then I say, but you realize this heuristic is not admissible. Explain how you know that this is not an admissible heuristic. And remember that an admissible heuristic is always less than or equal to the optimal cost to get to the goal. And it turns out that if we just sort of label these, if we say, let's call that toy 1 and that toy 2, maybe I'll put an arrow here, so, and an arrow here, so this is 2, right? So, see labels on toys above, right? And now I need to keep this here, but so let's see. So the Manhattan distance between the player and T1 is, well, what do we got? We got to do Manhattan distance, so it's 1, 2, right? And the Manhattan distance between the player and T2 is, let's see what we got here. We got 1, 2, 3, 4, right? But the optimal path to goal costs, and remember on problem 3, we were back to each move costing a point again, right? So, and you can go in all of those compass directions, right? So what have we got? So the optimal path to goal, well, here, I'll just write it first, right? Would be, let's see, first you go southeast to get this duck, right? So southeast. And then you would go southwest, southwest. and then west. Is that right? So southeast, and then we got so you go southeast, and then southwest, southwest, and west, right? And that is 1, 2, 3, 4 equals 4 steps, but MD equals 2, but the sum, okay, you can't do it about, right? The sum of MD of PT1, well, but MD of PT1 plus MD of PT2 above equals 6, and 6 is greater than 4, so H of S is not admissible, right? And different people gave different examples, but I tried to give you an example that you could just do. Isn't that a nice example? Okay. Okay, so here's problem 4. It has to do with breadth first search without multipath pruning. It says consider the graph shown over here. S is the start state. G is the goal state. And the question says, what data structure do you use to hold the frontier in for a breadth first search? And that's just a queue. And now part B says, fill in the frontier for steps 2 through 4. I gave you the first step. In the table below using breadth first search, and it says without multipath pruning. And then it talks about what you do for ties, but essentially you always add things in alphabetical order. So we started with S, right? And now we're going to pop S off of the queue, right? Because S is at the front of the queue. And look, it says put the top or front. So we'll just say front of your data structure on the left. And so now we're going to put an SA onto the queue. And I really don't care how you notate that. But there's my SA. And then we've also got an SB, right? And so now I take the SA off and I expand the A. So I've got A goes to B and A goes to C. So my SB moves up to the front. And then I have SA, what did I say? SAB and SAC. All right, so that was step 3. And then for step 4, the SB comes off and B, let's see, goes to A and D and G. So we have to first have all this stuff moves along. So we have SAB and SAC and oops. And then what did I say? We had SB, so we have SBA, A, B, C, D, SBD, and SBG. So that's what I was looking for this part. For the final question, 4C, it says, what final paths with a breadth first search without multipath pruning return for the graph above? And the answer is, there's 2 ways to do this, right? One way is you could step through this and show all of the steps. I didn't actually expect you to do that for this one because since it's breadth first search, it's going to, without MPP, without multipath pruning, it's going to find the shortest path, and the shortest path is very obviously this SBG. So for this one, because that was sort of totally doable without any steps, I fully accepted SBG. And if you wrote something like because BFS without MPP always produces an optimal solution, and this is shortest solution. You can't see what I'm writing anymore. Right? And there are no others of this length. So therefore, this is the only solution. So bing, bang, boom, you're done. Okay, so this is a similar graph. Problem 5, A star search with MPP. It says, consider the graph shown in this figure. It's similar to the previous figure, but there's no arcs between A and B. And I also added weights to the graph. S is still the start state. G is still the goal state. And the heuristic function is shown on the table on the right. So start actually has a heuristic of 10, and A has a heuristic of 0, and B is 12, and C is 4, and D is 6, and G is 0. Okay, good. And it says, what path would an A star search with MPP return for the graph above? So in order to get full credit for this problem, you had to show me some evidence that you had actually, you knew what A star search was, and that you were actually going about the right way to find the answer. Because there's only 3 possible answers for what's the path, and it's likely not going to be the optimal path, because otherwise, why would Dr. K ask us this? And I did say, before you took the exam, please show me work, show me your work, show me your work. So, let's see. So we've got sort of the path, and we have explored, and of course, A star search is going to use a priority queue, right? So we're going to start with just S on the stack, and it's the value of its heuristic. So I don't know how to do this. We'll make it a tuple with a value of 10, right? And then we expand S. So we'll say that we've explored S now, right? And what do we got? We have SA and SB. And SA is 2 plus 0, right, to get that function, right? So we've got, sort of the F of the path SA is equal to the cost of that path plus the heuristic of A, right? The last thing. So we need to figure that out. So we have, let's see, I'm going to just write them down. What did I say? It's 2 plus 0 is 2. So our new path is, I'm just going to write it like this. There we go, SA2, right? And then our other one is SB, which is 1 plus 12 is 13. So we've got SB 13. And this is supposed to be a priority queue, so we take the thing with the lowest value, which is the 2. So we're going to expand the A, right? So A is now explored. So strictly speaking, you need S and A now, but it's fine to just sort of show me your work by just writing the A there. So we've got, what do we have? We have SAC, that's the only thing. So SAC is 2, plus 1 is 3, plus 4 is 7. So we're going to add on here a 7 to this thing. So we'll have SAC 7 along with our SB 13. So now we expand the SAC, and so C goes onto the explored list, and the SAC is going to have value 2 plus 1 is 3, plus 3 is 6, plus 6 for the heuristic is 12, so that's still going at the front of our priority queue. So we have SACD with a value of 12, and our SB with a value of 13. And so now we are going to pull this guy off. And of course, D is not the goal. We always have checked when we pull something off, is that the goal, but it's not. So D is now also expanded, and we have D only goes to G. So, and if I do that one, it looks like it's going to be bigger than the SB now, right? So I have 2, 3, 4, 5, 6 plus 14 is 20. So I will have SB, which is 13, and then SACDG, which is 20. Right? Okay. So now it's time to expand the SB. And what do we got? We get SBD and SBG. Looks like D is smaller. And all right, so SBD is going to be 1 plus 2 is 3, and 6 is 9. So that's definitely going first. So we've got, let's see, SBD is going to be 9. And SBG has a 25 in it, so this guy's coming next. So then we've got SACDG. And oh yeah, I'm expanding B now, right? And SACDG is 20. And then we've also got on the same line SBG. So what's that? SBG, which has a value of 126 plus 0. So it's 26. Right? Okay. And maybe I'll draw a line there so you can tell what's going on here. There you can just about see everything. Okay, so we want to expand SBD. We pull it off, but we say, oh, look, D is already on the explored list. So we pull it off and we just toss it. So now we have SACDG with 20 and SBG with 26. And so now we pop off this SACDG. We add G to our explored set. And we say, oh, look, G is the goal, so this is my solution. So the answer to the question, what path would it take, is SACDG, right? But you only got credit for that if you showed me that you did some pruning, you did know what was going on with this. Okay, so this next question has the graph and the heuristics functions from the previous page are included here for your convenience, so this is a copy. And the first question is the heuristic function given above admissible? Justify your answer. So what we need to do is we need to show that all of the heuristic values, right? So we need to show that h of x is always greater than 0, and h of x, that's an x, is less than or equal to the optimal cost to goal, right? And so to do that, you can't just say, yes, it's admissible because I'm going to say this is true. You need to somehow show me. So let's see. Let's write an optimal cost to goal sheet here, right, for each of these steps, right? So obviously for G, it's 0. If I'm at state B, there's 2 paths, but 16 is obviously better. If I'm at S, it looks like 1 plus 2 is 3, plus 14 is 17, right? That was at S. And that's the best path, right? Because 1 plus 2 is shorter than that. So S, what did I say was 14, 15, 16, 17? What do I got to do? A. If you're at state A, you don't really have a choice of path. So it's 4. Sorry. Yes, if you're at A, 1 plus 3 is 4, plus 4 is 8. 14 is 18. If you're at state C, it's 3 plus 14 again, not much choice, so it's 17. And if you're at state D, where are you? It's 14. That's the only choice you have, right? And so now what you need to say is, are these all greater than 0? Yes. Are all these greater than 0, right? These are my heuristics. greater than or equal to 0, yes, because that's equal to 0, that's equal to 0, that's okay. And then you say, okay, are they all shorter than the optimal cost of goal? So you say 10 less than 17, 0 less than 18, 12 less than 16, 4 less than 17, 6 less than 14, 0 less than or equal to 0. So we're good. So what you need to do is you need to say, yes, the table above shows that h of x is less than or equal to the optimal cost, and all the heuristics are greater than or equal to 0, right? So you're good. For the other question, is the heuristic function given above consistent? Justify your answer. There's two ways you can do this. One way that is perfectly fine is to say, no, in the previous problem, no, let's say the optimal path cost for S, is for S, B, D, G, is 17, right? But A star with MPP did not find that path. That's perfectly acceptable. Or the other thing that you can do is you can say, so that's one option. And the other thing you can do is you can say, okay, can I fit this in so you can still see the picture? Sort of, kind of. There, you're going to have to look at an angle or something. Well, I'll write it up here so you can see the picture, right? Here. Sorry, give me a second. I gotta get a different color pen. Here we go. So this, you can't see it, just gonna start down there, right? I'm gonna do it up here, but so this is the other optional answer, is a heuristic is consistent if for all edges from n to n prime, h of n is less than or equal to the cost from n to n prime plus h of n prime, right? That's the definition of a consistent heuristic. And there's a couple of examples here that that do not meet that. So if we just look from start to A, let's see. So the edge from start to A, h of s equals 17, and the cost of s to A plus the heuristic at A, let's see, cost of s to A equals 2, right? 2. And the heuristic at A is 0, and 17 is greater than 2 plus 0, right? That's there. And so this does not hold, right? So that's the other way you could have done it. Okay, so this problem asks you to do minimax with alpha beta pruning. Do a minimax search with alpha beta pruning on the graph shown below. As you do so, draw an X through any branches that are pruned, and also draw an X through any leaves on those branches that are not visited, just to make it obvious. And then there's a couple more questions, but I expected, I mean, I've given questions like this on previous exams, and I gave you, the opportunity for a cheat sheet, so I expect that you have something like this somewhere, right? Or you've memorized it if you feel like it, but that's fine. But we always start, when we start our minimax, we're going to start it. See if I can show you this. I'm not sure if I can. Yeah, no, you can't really see it. Let's see. It doesn't matter, right? So we're starting out with max, right? State, alpha, beta. And our state is going to be, we're going to start with that state, and we initialize everything going off with alpha as negative infinity and positive, and beta is positive infinity. So, we've got alpha equals negative infinity. We've got beta equals positive infinity. Right, and then we also, each time we run this, if we're in here now, we create a new v, which is negative infinity because it's a max state. And then what we need to do is, for each of the children, we need to take the max of the min values of these, right? So we need to run the min value function. So we're going to call min value, right, on this state now, right? And we've got alpha is whatever it was up there. We passed it down, negative infinity. Beta is infinity, right? And then we start with v, and v, in this case, since it's a min node, also goes to infinity. And we're going to call max on each of the children of that, right? So we run the max, and we get alpha is negative infinity, and beta is infinity, and we initialize v to be negative infinity, right? And we run min on all of the children of this node, so we'll start there. And so alpha starts out as negative infinity, and beta starts out as positive infinity, and v, because it's a min node, right? I'm doing this one. Can you see all this? Yeah, you can, sort of. Can you hear me? Yeah, look, the microphone is going. V it's a min node, so V starts out as positive infinity. And for each of these states, we say, oh, look, we can finally run it. So we're going to take the min of max on this guy, which is just 2 because it's a root node, right? And so we are going to say, what is the min of V, which is infinity and 2? Well, it's 2, right? And then is V less than or equal to alpha? No, V is not less. That's a negative infinity, right? V is not less than alpha. So beta gets the minimum of infinity and 2. So beta is going to be 2. And we repeat for the next child. So now we have 3, right? So 3 is the value. And it says V gets the minimum of what V already is, which is 2. And this 3, well, so V is just going to stay at 2. Is V less than alpha? Nope, still not less than alpha. So beta gets the minimum, stays the same. And so we're going to return V. So 2 is what's getting returned from down here, right? And so now what we're going to do is we're back up here. We're in this node, right? We got a 2 back up. And so we are running in a max node. So we are running the max algorithm now. Can you see this? There we go. And so for each successor of state, we just figured out what the min value of this is. It was 2, right? And we say, what's bigger, right? Because V is going to get the maximum of 2 and negative infinity. Well, it's 2. So we will take that 2. And then is V greater than or equal to beta, which is infinity? No. So alpha is going to get the max of negative infinity and 2. So we like alpha 2. And now we will try, right, we're in the for each successor of state, so we will run this on the second child. It just returns a value of 10, and we are going to pick the maximum, right? V gets the max of the current V, which is 2, and this one, which is 10, so you cross that out, and there's a 10. Is V greater than or equal to beta? Nope. So alpha gets the maximum of 2 and 10, so alpha becomes 10. Right? And then it says return V. So we're going to return what's V? It's this 10, right? Because we've gone through all the children now, right? And so that 10 will come up from this node. Now, we are in here. And this node was running min, right? And it said, figure out the max of this guy. Well, we did. We got 10. And now we need to know what's the min of v, right? The current v, which is infinity, and whatever we got, which was 10. And 10 is smaller, so v is now going to be 10. And is v less than or equal to alpha? No, alpha is negative infinity. Remember that alpha is always sort of the best we've seen so far from above for max, and beta is the worst we've seen from above for max, or the best for min. Anyway, so v gets the minimum of that. Is v less than or equal to alpha? Nope. Beta gets the minimum of b and v, so beta is going to get that 10 as well. So now we've got beta is 10. And now we run the same thing on the next child, but notice we get this, we're passing down now. Alpha is still negative infinity, but beta is 10, right? So we are going to run the min on here with an alpha is negative infinity and beta is 10. And it says for each of the children of the state, right, we are going to say v gets the max of, figure out the min of, right, run min on this, but it's just a constant, or it's a leaf node, so we just pass that back, that 11, and it says v gets the maximum of whatever v is right now, which is, let's see, oh, we had to initialize v up here in our max to be negative infinity. Sorry, I didn't do that. Okay. V gets the maximum of negative infinity and 11, so v becomes 11. If v is greater than or equal to beta, look at that, 11 is greater than or equal to 10, which means that there is no way that this min node would choose this path, because it knows it can get 10 on that direction and 11 now on this direction, which means that we just return v up. So we're going to send that 11 back up right now, and we're going to cross off that edge. And I'm also just going to say, look, we're not going to use this guy or that guy either, because the instructions told us to draw an X through any branches that are pruned, and also draw an X through any leaves on those branches that are not visited, just so that I could be sure that you know what you're doing. So we returned the 11 up here. This is a min node. So it says v gets the minimum of the 10 that we had already and that 11, so v stays the 10. Is v less than or equal to negative infinity? Nope. So beta gets the minimum of this, it's still 10. And we return v, so we're going to return a 10 coming up this way to the max node. We are in the max node now, right? So running this function, so v is going to get the max of negative infinity and 10. Well, that's 10, right? Is v greater than beta? No, it's not, because beta is still infinity. So alpha is going to get the maximum of negative infinity and 10. So alpha is now 10. And now when we run the min value on the next successor down this way, we're not running it with negative infinity and infinity, we're running it with 10 and infinity, right? So we'll come down here to run this min function where alpha is 10 and beta is infinity. And because it's a min node, can you still see this? No, not quite, but almost. I don't know where to put it, I'll put it there. Because it's a min node, we initialize v to be positive infinity, right? And then it says take the min of the current value of v and run max on this guy. Oh, look, it's a leaf node, so we'll just get that 5 back. And it says v gets the minimum of infinity and that 5. So v is going to not be infinity anymore. It's going to be 5. And if v is less than or equal to alpha, ooh, look at that. 5 is less than 10, right? So that means that max knows it can get 10 if it goes left. And the min could pick 5. So we know that this path is going to be less than or equal to 5. And so it says if v is less than or equal to alpha, it is just return v. So we're just going to return the 5 back up, which means that this is where we're pruning, right? So nothing under there is going to get taken. So this guy isn't going to get looked at. None of these ones are going to get looked at. The 5 comes back up. We are in a max node, and it says, right, V gets the maximum of our current V, which is 10, and the V that we got from here, which was 5, so we got the 5. Is V greater than or equal to beta? Nope. So alpha gets the maximum of A and V, so alpha stays as the 10, and magic presto changeo, we return V, so we return 10. So what does Max expect to get? 10. What direction does Max expect to go in first? Left, right? Because those are these questions. And to get full credit for this first part, to get full credit for 6A, you needed to show me not only that you crossed off the right branches, but also you had some indication in here as to why you crossed those off, right? So I gave you some credit if you got them, but if you didn't show me any work, then I did not give you full credit for this problem. Okay, last problem. To do with CSPs. It says you find the following puzzle in a magazine. Find values for A, B, C, and D such that each of them takes on the value of a digit between 0 and 9. No 2 letters have the same value, and they make the following math problem true. And then I give some examples. You could, of course, solve this by trial and error. For example, here's 2 possible solutions, right? If A is 1 and B is 4, C is 2 and D is 6, then you get 1, 4 plus 2, right? AB plus C equals 1, 6, AD. And also if A is 3, B is 4, C is 5, and D is 9, you get the solution. But you've just learned about constraint satisfaction problems in your AI class, and so you decide you're going to formulate this problem as a CSP, so you can use a generalized arc consistency algorithm to solve the problem. And I don't actually ask you to solve the problem using GAC, but I do ask you a few questions about this. So part A is, what are your variables? And the most obvious solution that I think pretty much everybody picked here is my variables are A, B, C, and D, right? What are the domains of your variables? Well, the domains for each of them are the digits 0 through 9. So, I mean, you could just write that, right? Each variable has the domain, and you could write, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. As a domain is a set. And what are your constraints? Well, let's look at the problem here, right? What do we need to know? We need to know that AB plus C equals AD, right? And so one way to write this is A times 10 plus B plus C equals A times 10 plus D, right? So there's one constraint. Another constraint is that none of the variables equal each other, right? So A is not B, and A does not equal C, and A does not equal D, and B is not C, and B is not D, and C is not D. I think I got them all, right? And this math equation works okay. I mean, for sure, I took off some points for people who said AB plus C equals AD, because that sure looks like multiplication. That's not what we're looking for. But if you look at this problem, really the A doesn't change, right? So really it's you want to know that B plus C equals D, but also super important, we're not doing any carrying, right? So the sum of B plus C is less than 10. So I was looking for constraints like these. And that's it. This was a pretty simple problem. Most people did pretty well on it.